Okay, so we're going to continue our investigation into connectivity with another flavor of connectivity, and in fact another beautiful theorem due to Menger. So you see I have the definition of a k-connected graph written here. A graph, as a reminder, it's k-connected if it has at least k plus 1 vertices, and it has the additional property that however you delete from the graph a set of fewer than k vertices, the resulting graph will always be connected. Now, maybe I'll just remind you, last lecture we proved that a graph is k-connected if and only, a graph on at least k plus 1 vertices is k-connected if and only if, for any two vertices, for any two distinct vertices, there are k internally disjoint paths between them. So that means k paths from one to the other, and when you look at any two of them, they intersect only at the ends. Now, that notion of connectivity that we have there, it's based on vertices, right? Our graph has the property that however you delete a small set of vertices, you stay connected. That's the key property in the definition. What we're going to do this time is we're going to look to an analogous kind of setting, but instead of deleting vertices to disconnect the graph, we're going to be deleting edges. So we're going to be thinking about how many edges do you have to delete in order to disconnect the graph. And that's going to lead us to another variant of Menger's theorem. Now, this is the edge version of Menger's theorem instead of the vertex version. Now, maybe say up front that in fact the good news here is that the edge version is just easier. It's sort of everything is kind of a half step simpler. It's a little cleaner to define, and the proof from the ground up is really like slightly easier. However, we've already done the vertex version. We've already done the heavy lifting, and so what we're going to do is we're going to deduce our edge version from that one. So we are, I have up here the definition of k-connected. The thing that we're going to be leaning on is that if a graph is k-connected, then for any two distinct vertices, you have, for any two vertices, you have k internally disjoint paths between them. And actually, I think we'll even be using the earlier version of Menger's theorem just because it's a little bit cleaner, and it's I hope you recognize it's equivalent concerning two disjoint sets. Anyway, so that's kind of the outline for today. We're going to be moving to this edge-based version of connectivity, and we're going to be moving to prove a Menger theorem in this setting, another nice theorem with a similar kind of flavor. But before we get going, I need to introduce some things. And because we kind of want to move from edges to vertices, we're going to because we want to move from edges to vertices and we're doing graph theory, we are going to introduce an important concept called the line graph that's going to kind of allow us to encode what it means for, encode the edges in a new graph in a nice way. So, okay, without any further ado, let me get rolling on the definition. So, if I give you a graph G, the line graph of G, it's going to be a new graph there's the definition. This is denoted L of G. This is going to be a simple graph with vertex set E, and it's going to have the proper. So if I tell you I'm making a simple graph and I've told you what the vertices of that simple graph are, I just have to tell you what who's adjacent to who, and that will define the whole graph, right? So here I'm now this gets confusing because there's a set of things that are vertices and edges simultaneously, right? So I'm going to be I have a graph G. E is the set of edges of that graph G. Now, I'm building a new graph called the line graph of G, and E is going to be the vertex set of that line graph. So the vertices of the line graph are the edges of the original graph. And now we're going to define adjacency in the natural way. The rule is that if you give me two elements of E, so those, as a reminder, those are edges of the original graph, but they're going to be vertices in my line graph. So E and F are going to be adjacent in this line graph if, well, we're going to go back and look at the original graph. There we see two edges, E and F. If those two edges have a common endpoint, then they're going to be adjacent vertices of the line graph. So if they have a common endpoint in the graph G, right? So again, we're going to start with the graph G. We're going to make a new simple graph called the line graph of G. The vertex set of the line graph is going to be the edge set of G. And the rule is that if you take two elements of that vertex set of line graph or edge set of G, they're going to be adjacent in the line graph if those edges share an endpoint in G. So let's just do an example. And let me comment ahead of time. This definition works for not necessarily simple graphs. For most of this lesson, for most of this chapter on connectivity, we've just been assuming the graph is simple because edges, parallel edges, and loops don't really contribute to the story. But here they might. So the line graph is a thing that we will take as defined for a graph G that's not necessarily simple. And I'm going to go ahead and show you an example where the graph G is not simple. So here's the graph G. Now, I really don't care what the names of the vertices of G are when I go to construct the line graph. That won't matter at all. So I'm going to give names to the edges because that's what I care about here. So there we are. So the my graph G has edge set 1 up to 8. And now I'm going to construct the line graph. Again, the line graph is going to have the property that the vertex set of the line graph of G is the edge set of G. So in this case, the vertex set of my line graph is going to be 1 up to 8. And I'm going to try and put these in the same, more or less in the same position as the edges. I mean, I can even, I don't really think about it. Maybe I can even sort of superimpose things. Let me try and be a little fancy here. So what I'm going to do is I'm going to draw the vertices. So again, I'm moving to the line graph. I'm taking the old graph here, G, and which is in green, and I'm going to be drawing the line graph in orange. And so my line graph here, again, the vertex set of the line graph is going to be the edge set of the original graph. So in this case, the vertex set of my line graph is going to be 1 up to 8, and I'm just going to be joining two of these elements if those edges of the original graph G share an endpoint. So let's go. So 1, you can see that the edge number 1 has two ends. There's an upper one and a lower one. At the upper one is that edge 1. Sorry, what am I trying to say? At the upper one, that you see the edge 1 sharing an endpoint with 2 and 3 and 4. So 1 is going to be adjacent to 2 and to 3 and to 4. Similarly, because that vertex is there, 3 and 4 are going to be adjacent, and 4 and 2 are going to be adjacent, and 3 and 2 are going to be adjacent. Now down at the other end of vertex 1, you see that there's a vertex there where edges 1 and 2 and 8 are all coming together. Where edges 1 and 2 and 8 are all coming together. So I'm going to have these adjacencies in the line graph. Edge 8 is going to share an end with edge 7 from the lower right-hand corner. The other end of 7 there you see edges 4 and 5 and 6 and 7 all coming together. So those edges all share an end. And what else do I have? So I also have, well, up here at this top vertex, you see edges 3 and 5 coming together. And I think I've got it there. I wonder how well this will work. Not too bad. Okay, so that's my line graph. It's my well, okay, I could change this all to orange. Yeah, okay, so there we go. So this is the line graph of G. Again, the definition's really quite simple. It's the natural concept of touching, right? If you I give you two edges in the original graph, you'd say those two edges touch or are adjacent if those two edges share an endpoint. We are just using that to build a new graph on the edges in the obvious way. So given a not necessarily simple graph G, we are going to form a new graph called the line graph of G that will necessarily be simple. And the rule is that the vertices of the line graph are edges of the original graph. Two of those elements, two of those vertices of the line graph, simultaneously edges of the original graph, they're going to be adjacent as vertices in the line graph if those two edges share an endpoint in the graph G. And this is what we get. And you'll see what we're doing here is we're encoding, you know, edge touching in the form of a new graph. And that's a really handy feature, especially for doing the kind of thing that I've outlined we're aiming toward doing today. Okay, so that's the line graph of a graph G, and now we need one more theorem here, or sorry, one more definition. If I give you a subset of vertices X, so G is going to be a graph. Again, this is not necessarily simple. And X is a subset of the vertex set V. Then I just want to give a name to the set of edges that have one end in X and one end outside of X. And I'm going to use delta of X to denote that. So we're going to define delta of X to be the set of all edges X, Y in edge set of G, such that X is a vertex that's in the set X and Y is not in X. Right. So this is easy enough. If I give you, I'll just draw a little picture. So if this is the set X, this is the complement of X, all these edges here, that forms the set delta of X. So delta of X are the edges that have exactly one endpoint in X and one endpoint in the complement of X. And any set of that form we call an edge cut. Any set of the form delta of X is called an edge cut. Okay. Oh, and one more little caveat that I have here that's just a bit of, we're just introducing for convenience. If I give you a single vertex, then our delta, you can ask for delta of the set of edges that are sticking out of that single vertex. But it's inconvenient to have to write set braces around it, and formally I would have to. So we're just going to define, if I say delta of a single vertex V, this is just defined to be delta of the singleton V. Okay, so I mean these are things we've seen edge cuts before, but I don't think we've named them. So here we have some name and some notation. So again, if I give you any subset of vertices X, delta of X is going to be the set of edges with exactly one endpoint in X. So they're sticking out of the set X. Any set of that form is an edge cut. All right. And now with that, we're finally off to the races, and we really are kind of off to the races here. We are really not going to spend that long proving our big theorem, because it's just going to come from the vertex version. But anyway, let me get it up here on the board. So this is Menger's theorem, the edge version. And here's the theorem. So now I'm going to give you a graph G and two distinct vertices, U and V. And again, I'm going to give you a non-negative integer. And then our theorem is the following. Exactly one of the following is going to hold. Exactly one of the following holds. So now, as I say, we're switching up from vertices to edges. I'm still giving you two vertices, U and V, and I'm now switching my perspective from vertices to edges. And what that means is that, well, instead of trying to find paths from U to V that are internally disjoint, I'm going to be looking for paths from U to V that are edge disjoint. They're not allowed to share any edges. So either there exist K edge disjoint paths from U to V. Right, so that's the edge version of what we were doing before, right? So before we wanted these, we were looking for paths, and either we had two sets of vertices and we wanted vertex disjoint paths between them, or I gave you two vertices and we were looking for internally disjoint paths from one to the other. But there we're looking for, we don't want them sharing vertices. Now we're relaxing that. So you see these, if I give you a family of edge disjoint paths, they're allowed to use the same vertex over and over and over again. They're just never allowed to use the same edge. And what should be the obstruction now? So, what's the natural thing that prevents you from having K edge disjoint paths from U to V? Well, a thing that would get in the way is if you had an edge cut separating those two vertices and the size of that edge cut was smaller than K. Right? If I have an edge cut of size smaller than K and U on one side and V on the other, then any path from U to V is going to have to use an edge in that edge cut. And so if you want a whole bunch of edge disjoint paths, well, you're not going to be able to find K of them if there were fewer than K edges in that cut. So that is a natural obstruction. I will write down, there exists a subset of vertices subset X of our vertex set V that contains U, but not V. And there are just not many edges sticking out of this set X. The size of delta of X is less than K. So, right. So again, I'll, let me draw a picture here. So for my two vertices U and V, either we get these, I realize I'm drawing them just vertex disjoint again. I can try and draw one or two that, these things end up getting pretty messy if you start drawing them sharing too many vertices, but either you get K edge disjoint paths from U to V, or there's an obvious reason why not, namely there's an edge cut of this form where you have less than K, right? So what I'm saying is, again, another really nice structure theorem. So I give you a pair of vertices, you'd like to find edge disjoint paths, that go from one to the other. Certainly natural structural thing you might want in a graph. This answer is as lovely as you could ever hope. For any two vertices u and v, either you get k edge disjoint paths that go from one to the other, or there's a very obvious obstruction that would prevent that from ever existing, namely there's an edge cut that's separating the two vertices with the property that the number of edges in that cut is smaller than k. Clearly, if that happens, you cannot find those k paths. So yeah, so here we are, another nice theorem of Menger, another nice if and only if. So by what I'm claiming here, the exactly is automatic. It's not possible to have two of these, have both of these conditions simultaneously satisfied. If you have this small edge cut, then you will not have your paths. So to prove the theorem, I may as well assume that all edge cuts have size at least k and try to prove that that this exists. So let me just say 1 and 2 can't hold simultaneously. So now let's so let's assume that 2 does not hold. So we'll assume the size of delta of x is always at least k. Well, sorry, I'm very short on space. Let me just assume 2 doesn't hold. And so I'm assuming that all edge cuts separating u and v have size at least k. And now we're going to try to show that you have these edge disjoint paths. But here's the good news. We can just pass to the line graph, and our problem of packing edge disjoint paths here is going to turn into a problem of packing vertex disjoint paths in the line graph. Okay. Oh, maybe what I should do is just erase the picture. Let me do that. Okay. Let me erase the picture. Hopefully you've internalized that. Okay. So so here's what we're going to do. I'm going to, as I said, move to the line graph, and we're actually going to be using the version of Menger that works for a pair of sets. I mean, I think of the version of Menger that works for a pair of sets or for a pair of non-adjacent vertices. I think of those as about the same. You can quickly get from one to the other. So what we're going to do is we're going to move to the line graph. We're going to consider the line graph of G, and I'm now going to define two sets of, well, these are sets of edges in the graph G, but there'll be vertices in the line graph. So I'm going to define the set A to be delta of U and B to be delta of V. Right? So again, maybe I'll draw a smaller picture if I can. So in our original graph, I have these vertices U and V. A is this set of edges, B is this set of edges. Now, what I'm going to look for in this line graph is a collection of K vertex disjoint paths from A to B. So, if the line graph of G has K vertex disjoint paths from A to B, right, so that's K vertex disjoint paths from A to B. In this case, my original graph G is going to have K edge disjoint paths from U to V. Why? What's going on? Well, in the line graph, we have these paths that go from the set A to B, right? So it's it's path that's given. I can distinguish it by a sequence of vertices. So those vertices in the line graph. They are edges in the original graph, and it's a collection of edges. And what do? You're going to start at some edge in A, and you have to move to an edge in B, and at every step you have to move to an adjacent to you have to move to another edge that touches the one that you're on, right? So in other words, if I think about a path in the line graph from A to B, again, what that's going to look like, like as always, I'm short of space here, but if I gave you let's say E1, E2 on up to E sub t is the vertex sequence of a path in L of G from A to B, if that's what I gave you, right, those are vertices of the line graph, then what would this look like in the original? Then, or in the original graph, maybe I'll even just try and draw it up here. In the original graph, you're going to start at some edge in A, and then you're going to move to another edge that shares an end with this one. So maybe you move here. At the next step, you move to another edge that shares an end with this one. Maybe you move here. The next step, you move to another edge that shares an end with this one. Maybe you move here. The next step, you move to another edge that shares an end with this one. Maybe you move here. You can see that if you're moving from an edge to an adjacent edge, moving from an edge to another edge that shares an end with it, you can sort of keep moving out like this in a fan, but well, either you're going to stop or at some point you have to start going out. But the short of it is that, and this is the key observation. The key observation is that any path from a vertex of A to a vertex of B in that line graph, that is going to contain the edge set of a path from U to V in the original graph. And because because we have K vertex disjoint paths from A to B, then we are going to get K edge disjoint paths in the original graph from U to V. So I mean, I'm just short of space to write anything out very properly, but so I'm just going to write the conclusion again. This is just an easy observation. You just need to think through and check this if I'm saying things too fast. But again, if the line graph has K vertex disjoint paths that go from A to B, then you just look at each one of those, a path from A to B in the line graph. That collection of vertices that you use will contain the edge set of a path from U to V in the original graph G, and that's going to give you K edge disjoint paths from U to V in the original graph. So if L of G has K vertex disjoint paths A to B, then G has K edge disjoint paths U to V. Otherwise, Menger's theorem for two sets applied in this line graph is telling us something lovely, right? If in this line graph we don't have that, then what happens? Let me draw a picture again. So then in the line graph of G, I would have a separation of small order here, so that A is a subset on the left and B is a subset on the right. So what this means is that, again, this is separation in our line graph. I have these vertices, right? Now, what's going to happen is if you delete this set of vertices in the line graph, then you can no longer get from anything in A to anything in B. And what that means when we translate this back, this means when I delete the edges, let me write, else there exists a separation let me say h1 comma h2 of line graph of G, order less than k, with A on the left and B on the right. And now we're going to define S to be the vertices in common. So S is that set of vertices in the line graph. When you go back to the original graph and delete that set of edges S, so S is a set of edges in the original, then you can no longer move from an edge in A to an edge in B along a path. So that means you have to have disconnected those things, and it means in particular that you will have disconnected the vertex U from the vertex V. So you'll have deleted a set of edges and you'll have disconnected U from V. And that means that you have to have an edge cut of size less than or of size strictly less than K that separates U and V in the manner described, right? If I delete a set of edges and you suddenly see that U and V are in separate components, well, okay, just file your components into two groups with U on the left and V on the right, and just that set of edges between those two from the original, well, that's an edge cut, and you deleted all of them by removing fewer than K, so that edge cut has size less than K, and that is that's our second outcome here. So again, what's happened here, I mean, I really don't say that much about this in the notes. Maybe I should have said something more, but I mean, this is one of these things where this is just an immediate consequence. It takes time to sort of step through and see why, but there's nothing deep that we're doing here. We have taken our problem about finding edge disjoint paths from U to V in our original graph G, and what we're doing is we're recognizing that we can encode this as vertex disjoint paths in the line graph from the set delta of U to the set delta of V. And once you see that, then all that we're doing is we're just taking our Menger theorem that we have for vertex disjoint paths between two sets, and we're just applying it in the line graph. It just translates back. As a result of that theorem, either you're going to be granted K paths that are edge disjoint in the original graph from U to V, or it's going to single out an edge cut of size less than K that separates your two vertices. So that's our Menger's theorem, and for the edge version. So it's it's super simple. I mean, you see here, like, the simplicity here. Remember when we defined the notion of a separation, that's kind of a notion that comes with some baggage and there's a bit to sort out. Here it's very, very clean. There's just an edge cut. Yeah, and again, so I give you a graph and two vertices. Either you have K edge disjoint paths from one to the other, or there's a very good reason why not, namely there's an edge cut of size less than K that separates those two. Okay. So thanks to this this definition, we're now going to define another kind of connectivity. We say the graph is K edge connected if, however, you delete a set of fewer than K edges from the graph. However you delete a set of fewer than K edges, the resulting graph is connected. So G minus S is connected for every subset of edges with size of S less than K. Right? So simple as that. So you're taking your graph, it's going to be K edge connected if, however you delete fewer than K edges, you will result in a graph that's still connected. And a quick corollary of that Menger's theorem is that a graph is K edge connected if and only if, for any two vertices, there are K edge disjoint paths between them. right? So your graph is going to be k edge connected if and only if for any two vertices there are k edge disjoint paths from U to V. Again, this is just straight away. If your graph is not k edge connected, that means there's a set of fewer than k edges I can delete to disconnect the graph. Well, if U and V are in separate components of the graph after deleting fewer than k edges, well, then you cannot possibly have k edge disjoint paths from U to V, because every such path would have to use one of those that I deleted, and we didn't delete. We deleted fewer than k. Conversely, if your graph is k-edge connected, then every edge cut has size at least k, and then it's straight from Menger's theorem that you're guaranteed for any two vertices k edge disjoint paths between them. So, right, so just like the vertex version, this edge version, very like kind of very appealing. Everything matches just how you'd want. The presence of these edge disjoint paths is a, it's a nice structure that you might look for, and it's automatic. You get it unless you have this obvious obstruction of an edge cut of size less than k separating your two vertices. Okay, so that'll do it for this lesson on edge connectivity.